morning to my dear Prof. Samadi, Director of Retail Innovation Center of Technology for Advanced Bioprocessing, UTM ICA. Mr. Charleston, Alliance Technical Tiam, researcher from All Cosmos Industries Sdn Bhd, distinguished guests from Madi Johor Bahru, Lembaga Perindustrian Dinas Malaysia, Department of Agriculture Johor, Jiwayu Micro Industries Sdn Bhd, and everyone. A very warm welcome to you all at our third lecture series entitled High Quality Fertilizer Towards High Yield and Safe Productivity by Mr. Charleston, researcher from All Cosmos Industries Sdn Bhd. We are very glad to see you here and appreciate you taking the time and effort to join us. Without further ado, we would like to invite on stage Prof. Dr. Muhammad Roji bin Samidi to present his speech.
Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Thank you, Ms. Zulaikha. Okay, welcome to ICA lecture series. This is our third in our series. So we are pleased today to have Mr. Charles. Mr. Charles has been with us for some time. He graduated from Bioprocess Engineering in 2009, right? With flying colours. And then he graduated his master's in Bioprocess Engineering as well in 2012. And he's currently Assistant Research Director of All Cosmos. Is that right? Okay. So we have been engaging in this area of soil health, soil wellness is quite some time since the inception of IBD. I think we have been focusing on the development of technologies to promote soil health, not only biofertilizer. So then later the years we collaborate with All Cosmos, and All Cosmos set up that in IBD, next building to N32. And we are pleased to have Charles to share with us the technology that he's been developing, the product that he's been offering to the farming community. I know they have a very successful brand, and we hope to have exchange of ideas how to develop not only high yielding, high quality, but also sustainable agriculture in the future. And I know it is a lot of interest by the members of the research community with regard to the new farmings. ICA was set up specifically to address this issue. There are a lot of opportunities in farming. Farming used to be viewed as something low tech, but now it is highly high tech, and of course it is so-called high return industry. So we have Dr. Chang, specialized in metabolism, and he is going to apply metabolism and system biology to agriculture. So with that, I would like to invite Mr. Charles to present your presentation. I hope you can share and we can have interaction during the lecture. So, okay, so thank you very much, Mr. Charles.
So very good morning to all esteemed guests. My name is Charles from All Cosmos Industries in Berhad. Today I will be talking a bit about fertilizer and how important fertilizer is in our community today. Because fertilizer is something that does not weave its way into our normal conversation. You don't sit around chit-chatting with your friend and start talking about fertilizer. It's something that people tend to take for granted, but it's something that is very important in each and every person's life. So before I start to move on more towards the importance of fertilizer in terms of sustainable agriculture, I would just like to give a brief introduction of how this particular word came about, when fertilizer started. So the concept of soil fertilization is not something that is new. It's not something that was developed in the 19th century. It's not something that was developed during the Industrial Revolution. It was something that dates back far beyond anything that we have ever thought about. It is something that actually started during the early human civilizations in Mesopotamia, even in Egypt. When people first found out that every time after the flood of the river Nile, the flood of the river Tigris, Euphrates, the crops, the yield increased. But why is this? This is something that for many years, ancient civilization, they know the importance of the flood, the annual flood. The annual flood will bring fertility. But during those times, nobody actually knows why. Why? But the flood helps. Well, why does the flood help? The flood helps by bringing nutrient-rich silt back to the soil. This is the basic fundamentals of soil fertilization. No application, it's just waiting for the annual flood. This is when it started. After that, you have the Greeks, the Romans, they found suddenly when they do crop rotation, the yield increased using legumes. But they don't know why. That is why after they plant cereals, they will plant these legumes like peas, soybeans. This is something that down the road, unfortunately, once they reached the Middle Ages, there was no progression. It was still the same thing. Crop rotations, waiting for annual flood, or maybe to some certain extent, the application of manure. Cow dung, chicken dung, all these type of things. But there was no real study or science to it. Why and how do we control soil fertility, and how does it impact the yield of the crop that we need? It was during the 1800s, the early 19th century, when people started to realize the importance of fertilizer. The concept of fertilizer, it was very much different from now and from then. It started with the concept of this Liebig's law, which states that even if one essential element is missing from the soil, you have all the other elements still in the soil, your yield will still be limited because there is still one essential element that is not there. And this becomes the basis of the entire agriculture industry up until today. Because if you have high nitrogen, you do not have phosphorus, you do not have potassium, still your yield will not amount to anywhere. So this is the basis from where it all started. And from here, then it progressed. And the first chemical fertilizer that was ever manufactured was actually made from bones. The bones of animals ground into dust and reapplied to the soil as the world's first phosphate fertilizer. Then down the road, they realized that this is very insoluble. You're not actually doing anything much because the phosphorus is still bound into the bone. So what they did after that, they treat the bone with sulfuric acid to release the phosphorus. Then after that, the Germans started to mine phosphate rock and started to treat phosphate rock with this sulfuric acid. And that is where we get the first superphosphate fertilizer. And further on, they reacted it with phosphoric acid, making what the industry is using today, superphosphate, the world's most used soluble phosphorus fertilizer. So this is actually where it started. And the significance of this is, the main significance of the entire fertilizer industry is based upon two major inventions. The first is the invention of the process to make, industrial process to make nitric acid. The second is the process, the Haber process, to make ammonia. Without these two things, we will not, our fertilizer industry will be very, very different today. We will not be able to produce urea, we will not be able to produce a lot of the fertilizers that we are using today. It is when phosphate rock is reacted with acidification of rock phosphate with nitric acid followed by neutralization with ammonia that we get the world's first mixed fertilizer. And then once you add in potash, that is NPK fertilizer. Fertilizer that contains nitrogen, phosphorus, and potassium. That is how the whole concept of NPK fertilizer came about. But the more important question is why? Why? Why was there a sudden emphasis in all this during from the 19th century to the early 20th century? What spurred these innovations? Because there is always something that is a driving factor. The Industrial Revolution did not occur because somebody suddenly thought about it. There was a demand. There was a demand for something. The demand here was food. Very simple, plain and simple. The world population increased tremendously from the early 20th century up until the 21st century. The world population doubled, tripled. And that was the reason why they were not able to sustain the food, because the yield per hectare is too low. They were not able to produce enough food to feed the citizens. So that is why the emphasis has been placed here. That is actually the exact reason why. Because there is always something. Without demand, there will be nothing. There is always demand. Once you have demand, the demand will spur innovation. This has been going on throughout all of human civilization. And since the 1960s up until now, there have been many types of fertilizers. You have the granular NPK fertilizers, you have polymer coating, control release fertilizers. There have been 1,001 different types of fertilizers that were developed based on the same principles, based on the same concept. But the emphasis, why there was so much emphasis on chemical fertilizers then, was because at that time the realization is that I can only improve yield by increasing the fertilizer input, by increasing the NPK that I provide to the plants. Then and only then will I be able to boost the yield. That was the primary concept. Very one-track mind. The more nutrients I put in, the more yield I get. There was no realization about the importance of biodiversity then. Then what happened down the road? Why was there a change? Why was there a change in the thought? Why today, whenever you mention the word chemical fertilizer, it almost always it equates to the word bad. Very bad for the environment, no good. But why do we think like that? 100 years ago, people did not think like that because the realization was that only nutrients are important. But now in this day and age, then we realize that biodiversity is equally as important as the provision of nutrients to the plants. What we did not realize is that one very simple example is that in Malaysia, biodiversity is going less and less. You see in oil palm plantations, when people first planted oil palm, the organic matter in the soil, that is what we call the topsoil, the most fertile region in the soil. The topsoil, it gets eroded over the years. Why did we see the effects now and not 30 years ago, 40 years ago, 50 years ago? It is because at that time, the topsoil was there. There was organic matter. And when you have organic matter, you will have beneficial microorganisms. You will have natural biodiversity of microorganisms that to a certain extent help plants to grow. What happens if you have too much of chemical fertilizers into the soil? Gradually we erode away the topsoil. The topsoil has been used and not replaced up until now. That's why in the whole of Malaysia you can see our most important crop, oil palm, the yield is dropping. Every year it's dropping. Even if you increase the input of fertilizer, it will still reduce because lack of biodiversity. The organic content of the soil has been eroded away, has been depleted, and that is why it is so important that we as a civilization now understand the factors, all factors that contribute to sustainable agriculture. That's why then we have this term sustainable agriculture. Before that, there was no such thing as a sustainable agriculture. There was only agriculture intensification. If I do not have enough, I plant more. I cut down trees, I cut down forests, I replace it. I replace the forest with the crops that I want to plant. And what does this lead to? It did not lead to higher yield, but rather it led to even more environmental consequences. The FAO estimates that the world population will, by 2025, will be around 8 billion. Which means we need to increase our food production by 75% by that time. How? How can we increase it when the yield now is going down? Among the challenges are shortage of fertile soil, increase agriculture in marginal soil. Because now you cannot just do agriculture in soil that is fertile. You have no choice. You even have to plant in marginal soil. Because that is the case. Because you need to feed everybody to prevent world hunger. And the increased use of chemical fertilizers, pesticides, herbicides, all this is leading to a very, very downward spiral. This is just an example of how dire our situation is. Because you see in 1995, our whole population 5.7 billion. In 2025, projected to be 7.9 billion. By 2050, 9.2 billion. Our yield is not getting higher. In order to meet this demand, there needs to be an annual increase in the yield by 1.75%. Are we able to achieve this by just using conventional chemical fertilizers? And I mentioned earlier agriculture intensification. It will only lead to more bad things like soil erosion, drought, desertification. This is something that is very, very serious in China. When you see even Beijing, which used to be a land that you are able to cultivate plants, is becoming more and more like a desert. This is something that is very, very, very evident. Desertification is one of the worst things that can happen to you. And you have pollution. Loss of soil fertility, loss of biodiversity, deforestation. And many a times we think that, oh, this is not happening in my country, this is happening somewhere else, this is happening in Canada, this is happening in US, this is happening in Europe, this is happening in China, it's not happening in Southeast Asia. But this is very wrong. Because this is a chart from the FAO. You can see that all the problems that I mentioned are all faced in Southeast Asia itself because of agriculture intensification. There is no sustainable agriculture. We plant and plant and plant. We cut down, we plant, we don't care. We just put in chemical fertilizers because all this stems from the fact that there is not enough awareness, there is not enough education. This is just a simple example of deforestation, loss of biodiversity. Actually, this is something that is actually quite sad in Malaysia. How much of our tropical forest has been converted into oil plant plantations, has been converted into rubber estates? How much of it be converted into a single crop, monoculture? We don't see, but because extinction of multiple types of microorganisms that we never even realize, and all these things, to a certain extent, has certain impacts to our environment. Erosion, desertification, pollution. How does chemical fertilizer pollute the environment? It pollutes it through two main mechanisms, by leaching. Actually, the main thing that leaches out is actually nitrate fertilizer. Potassium does not leach out. Phosphorus does not leach out. But why, when we apply a lot of urea, when you apply a lot of ammonium sulfate, you apply a lot of inorganic nitrogen fertilizers, why does the soil fertility go down? It is because the most soluble among them is nitrate. Once nitrate leaches down the water table, it creates an ionic gradient, a charge gradient, whereby the negative charge is at the bottom. So what this does is, this gradient would make even the positive ions go down to achieve equilibrium. So when this happens, not only do you lose the N, you also lose the positive ions as well. And that's why when you apply too much of nitrogen fertilizers, you would get the soil nutrient deficiency, because the other nutrients would go along with it. And in Malaysia, leaching is not so evident because we are a tropical country. Tropical country, you have tropical weather. The rainfall here is much higher than in temperate countries. Once it rains, it really pours. If you put in chemical fertilizers today, it rains in the afternoon. Tomorrow, gone. This is what we call surface washing. All this, again, will be washed into the water table, which will pollute the water supply. And once you get a lot of nutrients in the water, what happens? Then you get massive algae bloom. Algae start to grow. And what it does is, then all other aquatic life will be impaired. And once you displace or impair one organism, it will affect the entire chain and cause irreparable damage to the environment. And that is why today we need to think about more sustainable methods in agriculture. How are we able to reduce the dependency on chemical fertilizers, but at the same time still provide nutrients to the plants? Because let's remember Liebig's law. You still need the essential elements. If you do not provide the essential elements, it will still not grow. So how are we going to provide the essential elements, such as nitrogen, to the plants? The one way is to incorporate nitrogen fixing bacteria into your fertilizer. That way, it will convert atmospheric nitrogen into nitrate, into ammonia, which will be converted into nitrate and then can be uptaken by plants. So this is one way, but this does not mean that you do not put in any chemical or inorganic N at all. We need to strike a balance. That is the key here. To reduce the dependency of inorganic N fertilizers, but also to supplement a portion of it using microorganisms. This is how we can reduce the dependency on inorganic N fertilizers. Because actually the definition of poison is any substance that is used excessively. Even sugar can be a poison if you take it excessively. That is why the same applies. It is only dangerous when you apply it excessively. So an example of nitrogen fixers are like Azotobacter, Azospiridium, Bacillus, Clostridium, Klebsiella, Lysine Bacillus. Why do we call it free living? Free living N fixers are nitrogen fixing bacteria that are living naturally in the environment, that we have killed out over the extensive practices of our agriculture practices. So these are some things that we can reapply to the soil to help improve the soil biodiversity. And you have symbiotic nitrogen fixers such as Bradyrhizobium, Rhizobium, Sinorhizobium. These symbiotic nitrogen fixers are able to form a symbiotic relationship with different plants. For example, like the peanut. Why when you take out a peanut root you see nodules there? Because Rhizobium is able to form a symbiotic relationship with the plant, forming a special structure within the plant that is capable of fixing nitrogen at a higher efficiency level. So all these are very important to our agricultural practices. So another type of microbe that we can incorporate into our fertilizer is phosphorus solubilizing bacteria. But why? Why do we need this type of bacteria? Because a lot of times we don't realize that naturally in the soil there is a lot of phosphate, but it's bound. In Malaysia we have acidic soil. In acidic soil, the P is bound by aluminium and ferrum to form a structure that is not soluble. And let's say in Africa you have alkaline soil. Alkaline soil, which means you have a high content of calcium. So calcium also binds with phosphorus, forming an insoluble structure. All these are available in the soil, but we are not able to utilize it because it is insoluble. It is not naturally released and available for the plants. So through the action of using phosphorus solubilizing bacteria, we are able to release the naturally occurring phosphate within the soil to make it available for the plants, and thereby reducing the dependency of soluble phosphate fertilizer. And another drawback is that using phosphate fertilizer, soluble phosphate fertilizer, is the price, because it's much more expensive. It is 2 to 3 times more expensive than rock phosphate, which is an insoluble type of phosphate fertilizer, which is the main type of phosphate fertilizer that is used in Malaysia. So we have seen through experience, we have seen a lot of farmers, they find there is phosphorus deficiency, so they dump in rock phosphate, tons and tons of rock phosphate. They just dump in, they don't care, they just dump in there. After 1 year, I can guarantee you the rock phosphate is still there, because it's not able to be released, it's not soluble. And then one way to release bound phosphorus is by using phosphorus solubilizing bacteria. This type of bacteria, it functions in 2 main mechanisms. The first mechanism is that it is able to produce an enzyme called phosphatase, which helps to solubilize, and also the production of mild organic acids. These two combined mechanisms, will allow the bacteria to be able to release phosphate that is naturally occurring in the soil. And similarly, potassium mobilizing bacteria. This is also a similar type of bacteria to that of the phosphorus solubilizing bacteria. But of course the mechanism is different. Like I mentioned earlier, phosphorus is often bound either by aluminium or iron in acidic soil, or either bound in alkaline soil by calcium. But unlike that, the world's most natural type of potassium is bound by silicate. It is in materials such as feldspar, mica, which is very, very abundant. So what this bacteria does, it is able to solubilize the silicate that binds the potassium, thereby releasing it from its structure and making it available for plants. But similarly, this is something that we can incorporate into fertilizer to reduce the dependency on inorganic potassium sources. But it is not a total replacement. Because in order to achieve high yield, you still need a certain degree of fast action. Because if you solely use microbes, of course, definitely it will be very good for the environment. But if you talk about dollars and cents, your yield will be lower. So that's why we need to strike a balance. We need to strike a balance between the usage of organic materials, chemical materials, and also effective microorganisms or beneficial microorganisms. So the first three main microbes that I've been talking about is more towards nutrient provision. It's still talking about the age-old idea that nutrient is the sole factor. It's a sole factor that is able to give you high yield. What we fail to realize is that pests and diseases are also something that is very, very significant nowadays, that is affecting the yield. Because if you are sick, you cannot perform. If the plant is sick, there will not be high yield. Even though how much fertilizer that you put in, if it's infected by a disease, the yield will still drop. So that is why it is also important to incorporate natural biocontrol agents that are all naturally isolated from the soil. It's just that all the while we kill off all this through the application of pesticides, herbicides. We put in so much of toxic material, carcinogenic material into the soil that they are no longer there. So how we can improve it is by by adding in it into fertilizer which is applied to the soil. So this is just an example of a type of a bacterial-based biocontrol agent. There are many types of bacterial-based biocontrol agents. This is just an example of them. This is Bacillus subtilis that is used to control the various fungal pathogens such as Fusarium. Fusarium is a very serious disease, especially in banana. And even to certain extent, chili, pepper is very, very serious. And rigidoporous lichnosis. This is what we call the white root disease, the causal agent of white root disease in rubber. A very, very serious disease, whereby this fungus, normally fungal spores are not able to germinate in the soil without coming in contact into the host. The pathogens are not able to germinate, it will remain in the soil. But in the case for rigidoporous lichnosis, it is able to germinate and form mycelia in the soil until it reaches the host and then starts to eat away and colonize the root of the host. So this is one of the very serious diseases that we have in the rubber industry today in Malaysia. As you can see from the photos, once we apply the biocontrol agent, there is a slight inhibition zone, which means the bacteria is producing certain antifungal compounds that are preventing the growth of the fungus. So this is a basic type of test that we can just use to evaluate whether a certain microbe has antagonistic properties against a certain type of pathogen. And then there is this strain called Hendersonia, which is actually a very good success story between Oxford and MPOB and IBD UTM. Because we developed this strain, this process, this product containing this strain, Hendersonia. Hendersonia is actually an endophytic fungus isolated from the root of oil palm. And why? Why is it important? How important is Hendersonia? Because a lot of we don't realize that the oil palm industry actually loses 1.1 billion ringgit in yield to this disease annually. This is a report provided by MPOB. Almost all plantations in Malaysia, to some extent, have this disease. Not the entire plantation, but to a certain extent, each and every single plantation has this disease. So this is something that is, so far, there is no cure. Trunk injections, even if we inject fungicides directly to the trunk of the plant, you will not be able to cure the disease because it will come back. So this is something that is very significant, and it's a product that we are very proud to be able to develop jointly together with IBD and MPOB. And the main function is that not only is it able to produce antifungal compounds, it is also endophyte. What does endophyte mean? Endophyte means that it is able to colonize the root of the target plant. And what is the significance of this? Once it is able to penetrate the root, it forms a protective layer so that when we treat the plants from early stage, the seedling, so to speak, pathogens will not be able to penetrate the root because the upper layer of the tissue is already penetrated by the Hendersonia, which constantly is producing antifungal compounds which inhibit other types of fungal pathogens from coming into contact with the root. So this is just some of the data provided by MPOB. The application of Hendersonia is able to reduce the disease incidence by 46%. Reduction of severity of polio symptoms by 35%, and reduction of dead ceilings by 60%. Still, this is not a cure, but rather more a prevention strategy. Because this is also something that we must always take in mind, that prevention is always better than cure. Because basal stem rot caused by ganoderma is like cancer. It's like cancer in human. It's a cancer to oil palm. Once you are infected, the chances of 100% recovery is very low. There are some cases that there is recovery, but not all. That's why we don't dare claim that we can cure the disease, but rather this is more of a prevention strategy. Which is why sometimes, something that is very important is that you may be able to have a very good product, but no matter how good the product, if the application method is wrong, the results will be different. You may be able to have a very good drug, but if it's administered in the wrong way, it may lead to different complications. So this is why, for us, we always recommend that biocontrol agents should be applied to plants during nursery stage or during the replanting stage when it's still young, not applied when the disease is already there, it's already half dead, then we start to apply biocontrol agents. Normally it does not work that way. So this is an example of the field trials that were carried out. Those that were treated with Hendersonia showed very little foliar symptoms, very little necrosis. But those that were not treated at all, withered within 1 to 2 months, withered and died. And another type of fungal-based biocontrol agent that we can incorporate into fertilizer is trichoderma. Trichoderma is something that is quite known in the industry now, because it is known for one thing. It is known for its versatility. It is what you call a universal biocontrol agent for fungal diseases, because it is basically a mycoparasite. What is a mycoparasite? Mycoparasite is a parasite that parasites on other fungus. This characteristic makes it a very good biocontrol agent, because it is basically a parasite of other fungus. So this is how does it become a parasite? How does it kill the target pathogen? It kills it through several mechanisms: production of non-volatile antifungal compounds such as peptidols, or what we call short-chain peptides that have antifungal properties, or production of volatile antifungal compounds such as ketones, aldehydes, and the exact type of compounds produced, it varies from strain to strain. And not forgetting, it also produces lytic enzymes that are able to degrade the cell wall of the fungal pathogen, such as chitinase, which is a key component in the fungal cell wall, chitin. So this is just another example of the use of trichoderma as a biocontrol agent for rigidoporous, which is the causal agent for white root disease in rubber, which I mentioned earlier. As you can see from the diagram, rigidoporous is basically white in color. Trichoderma is green in color. And once we put the two together in the dual culture assay, you can see that the trichoderma is actually colonizing the colony of the rigidoporous, which indicates and proves the microparasitism activity that it possesses. And this is also another example using Phytophthora. Phytophthora as the fungal disease and trichoderma as the biocontrol agent. Phytophthora is another broad spectrum pathogen which has multiple complications in a wide variety of plants. You know, Phytophthora itself is a very, very large genus consisting of multiple types of fungal pathogens that are able to cause diseases in multiple different types of different crops, be it from chili, black pepper, or even fruit trees, mango, durian, rubber. There is a species of Phytophthora that can infect all of them. And I've been talking a lot about fungal diseases. Fungal diseases is not the only type of disease that affect plants. We also have pests, such as nematodes, such as locusts, such as rhino beetles, that also cause diseases in different types of plants. And this is also another type of biocontrol agent, metarhizium. There are also many different types of biocontrol agents that are able to control various insect pests, such as metarhizium is one of them, but there's also Bovaria marciana. There's also Pasilomyces delacinus, and there is also Bacillus firmus. This is just to illustrate some of the type of fungal-based biocontrol agents that we can actually incorporate into our fertilizer to not just provide nutrients to the plant, but also to provide a certain degree of biocontrol activity as a protection to the plant. And not forgetting, we also have another type of disease caused by bacteria. It is often very difficult to control bacterial diseases using fungus, because a lot of times bacteria have antagonistic properties towards fungus. So how are we able to control bacterial-based diseases such as Ralstonia, Xanthomonas, Erwinia, all these type of bacteria? Is by using what we call a bacteriophage. bacteriophage is a virus that's specifically targeting a specific type of bacteria. So it leaves out the rest of your nitrogen fixers, your P solubilizers, your K mobilizers. There's basically no effect because it only recognizes that particular type of strain. If you have a phage for Xanthomonas campestris, it will only infect Xanthomonas campestris. If you have a phage that is solely for Ralstonia solanacerum, so it will only affect Ralstonia solanacerum. It will not affect other types of bacteria. So it will not cause much of an impact to the biodiversity of the rhizosphere of your particular crop. So this is something that we can also incorporate into our product to provide a universal solution to sustainable agriculture. So how it works? It works by injecting its DNA into the target bacteria and then forcing it to replicate continuously until cell lysis occurs. This is basically how it destroys the pathogen. And one little seed culture is able to kill the entire population of the target pathogen, because that is how virus is spread. Regardless whether it is for bacteria, it is for animals, it is for humans, it is contagious. Once you come into contact, it will continuously replicate. And this is why is it significant in eradicating certain diseases? Because it will continuously multiply up until the point whereby there are no longer target cells. This is one of the advantages of using bacteriophage, and it will not cause any harm to humans. It will not cause any harm to animals. It will not cause any harms to plants, because how does the bacteriophage recognize the target pathogen? It recognizes it by certain receptors or that vary from microorganism to microorganism. That is how it recognizes the host. And by incorporating this type of material into a fertilizer, we will be able to improve the yield by also improving the biodiversity and also preventing diseases. This is one way. This is not the only way, but this is one way to improve the yield of crops without sustaining high environmental impact. So this is an example of the clear zones indicate the filter paper in the center is actually deep with the solution of the bacteriophage. So you can see the target strain. You see a clear zone, which means cell lysis has already occurred. So and the clear zone will only get larger. This is actually how the bacteriophage works and how it spreads. So these are just a few data that we've did over our course of our research. And from the photo you can see that the plant that was solely treated with Ralstonia solanacerum, a very, very devastating pathogen in tomato, and the one that was treated with Ralstonia solanacerum and also treated with phage. After 7 days, wilting occurred. Wilting occurred in the plant that was treated with was not treated with the bacteriophage. So this is just a visual representation of actually how it works and the effects that you can see. This is just to visualize it. And at the end of it, I've talked about the importance of the chemical side. I've talked about the importance of different microorganisms. But at the end of the day, there will be still 3 different types of fertilizer. You would have chemical fertilizers, you would have organic fertilizers, and you would have biofertilizers. Biofertilizers are microbial inoculants, solely consisting of microbe. There are actually 3 different types of fertilizers. So the key here to have a very good product is to be able to incorporate all 3 materials into one body. that is how we are able to produce a product that is having multiple functions, that is not just able to provide nutrients to the plant, but to a certain extent, slowly recondition the soil, slowly repair the damaged biodiversity, and also prevent diseases. The key here is to combine all three materials. And there have been many studies of how, because different, and this is not something that we can claim that is already perfect. This is something that is improving over time, because there are still some microbes that are not able to survive this process. So that is why there is continuous study in encapsulation. There is a lot of study regarding encapsulation. How can we encapsulate and protect the beneficial microorganisms that we want to use, so that it does not get killed off by the other chemical materials in the fertilizer. This is not something that we claim we can 100% do it perfectly, but it is still ongoing. There are certain strains, especially strains that are more tolerant. Strains such as bacillus, which are spore formers, which are higher tolerance. Strains such as trichoderma, which are producing high resistant aerial spores. This, so far, that is why we always hear of these few microbes: mycorrhiza, trichoderma, bacillus. There are so many other types of microbes that the function could be better, but the only problem is that we have not found the correct formulation or the correct method to encapsulate and incorporate it into fertilizer. But this is an area of research that is gaining more and more traction. More and more emphasis is being directed towards the biotech side, the microbial environment side. How are we able to make sure that the microbes that we put into fertilizer survive? Because if we just take chemical fertilizer, organic fertilizer, and then biofertilizer, we put all three together, you may not get the same results, because there must be a right dosage. It's always the general logic is that the higher the chemical content, the lower the survival of the microbes. So that is why it is very important that we incorporate carriers into the fertilizer, such as the organic material that is shown here. Because this carrier are the material that not only provide sustenance to the microbes, they also, to a certain extent, protect the microbes from coming into contact with the chemical materials. And there are so many different types of carriers that we can use, be it organic or even inorganic. Because there have been studies that show that vermiculite can also be a very good carrier, zeolite can also be a very good carrier, talc powder, talcum powder, can also be a very good carrier for certain and different types of microbes. So this is something that our company, All Cosmos, feels that is something that is very, very necessary. Because in terms of long-term sustainability, this is something that we need to do. And we cannot say we don't apply chemical fertilizer at all, we don't provide urea, we don't provide this. Because if we completely remove this, the whole world will starve. But what we can do is, we can gradually change the way, the mindset, the practices that are happening all around the world. This is something that we can do. So, by that I end my presentation. So I would like to welcome any questions from the floor. Any questions? Yes.
Thanks a lot for a very nice presentation. I have one very simple question.
Yes.
And one a bit complicated.
Okay, no problem.
So, how would you do the bacteriophage targeting? Right? Can every bacteria be attacked by a bacteriophage?
There is, for every bacteria, there would be a different type of bacteriophage that targets it. So it's very, very specific.
Yeah, but how would you
Yes.
screen?
Yes, that is a very good question, because that is where it is very, very tedious. Because once how we isolate bacteriophage is very much different than how we isolate any other thing like trichoderma. Because once we isolate, there is a certain protocol to isolate bacteriophages, but we must always use the actual pathogen as the determining factor. If there is no clear zone, there is no cell lysis, meaning you have bacteriophage but it's the wrong bacteriophage. So you need to repeat the cycle over and over and over again until you see a clear zone.
So it's more like a trial and error.
Yes, yes,
The other thing, we all know about viruses.
yes,
They have no proofreading enzyme, right?
yes.
You never know when there's a mutation and they lost
Mm-hmm.
affinity for the specific receptor on the bacteria.
Yes,
And somehow, but there's also a chance, because there are spontaneous mutations in bacteria,
yes,
they change their
Yes.
receptor,
Mhm.
and then you have an epidemic.
yes.
Something happens.
Yes, this is also a very, very good question, because this is also something that is asked by the Ministry of Health, which is why for bacteriophage products, we need to go through a very long period of testing and a controlled environment of testing. It's not if I isolate today, tomorrow I can sell. No way. Require around 5 to 10 years to see actual, are there any mutations? Are there any changes? Does it work for the first 3 years and then after that you create something even worse? Because if we don't have this data, this is something that we cannot sell. So this is very good point, very, very important.
This is a very attractive, potentially a very good way. I mean, fantastic. The last question is about zeolites.
Mm-hmm.
This is something that really fascinates me, because
Mhm.
I'm a nanobiotechnologist,
Mhm.
and I know about zeolites.
Mm-hmm.
So how would you do the encapsulation in zeolites? Because in my project, we partly work with zeolites in
Mhm.
Holland. It's very difficult to you can put inside anything you want in the holes, right?
Mhm.
So it's a silica,
Yes.
like it's silica and
Yes.
tubes. How would you confine them in the zeolite space? What other nano platforms can you use for this encapsulations?
Mhm.
Polymers?
So for us is not, we don't go until to that particular extent. What we do is we add in certain adhesive, such as polysaccharides, to help it adhere better to the carrier. And one of the reasons is that because there is still not enough testings regarding this, that is why reproducibility is a major issue. Sometimes when you do the QC test, you get a higher yield. But sometimes when you do the QC test, you get a lower yield. So this is something that is, because we don't fully understand the structure of the material and how, when we add in the adhesive, what is the correlation between what we add in to how is it being retained. So this is just more or less of a simple study that we do. We found that there will be always a range. When we add in, let's say, alginate into when we do the encapsulation, we get a yield that range from A to Z. What we found that this is the tolerance, but to exactly get the exact figure that we want, and also to truly understand the mechanism of how it's being adhered onto the material, this is something that I cannot answer you yet.
Okay, thank you.
So any other questions from the floor? Mm-hmm. Mm-hmm.
organic fertilizer. Because
Okay.
our plant, our area is within the soil, but this is the housing area. So right here, when I apply the fertilizer, currently I'm planting here. The flow is really, really good. But the roots here is very simple. You don't get yam, but the leaf is growing. Is it because of the lack of soil?
I'm not a soil specialist, but I will try my best to answer your question. Normally, if you have a very high vegetative growth, meaning is nitrogen is too much, and because the most important element for root development is still phosphorus. So I'm guessing that maybe the formulation may not be the optimal formulation for production, because sometimes there are cases that when we apply the raw fertilizer, we don't get the yield, but we get one very, very big tree. The leaves are fantastic, but there is no yield because maybe certain elements are not at the optimum formulation. I'm not too sure of the formulation for this. I have to refer back to our company's agronomist. Mm-hmm. 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 Mm-hmm.
Fungus can produce antimicrobial, antibiotic complex, antibiotics, and then
Yes.
bacteria will produce antiviral. Is that true? This is from the system biology.
Theoretically, yes, but many a times, yes, they produce, but again, the susceptibility of different microorganisms may be different. Yes, we have actually isolated penicillium before, but we tried to use in theory, penicillium produces penicillin, which is antibacterial. But when we use it against our Xanthomonas campestris, nothing happened. There's nothing happened. Because this is something that we don't truly understand. The degree of resistance, the biodiversity of the particular pathogen itself, it could vary. It could vary from when the place is being isolated, because they could have undergone certain mutations, they could have the resistance. This is something that we don't know. And there are also times whereby we test on, let's say, 3 different types of Ralstonia. It can inhibit 2, but there's one that it cannot inhibit. So this is something that is quite difficult to address, because we don't fully understand. We don't fully understand the target microorganisms that most of the time we are talking about. Because let's say we're talking about Xanthomonas campestris, it is same like Homo sapiens. There are 7 billion of us. Not every one of us are the same. If it so happens that you isolated one that has a resistance to a particular type of antibiotic, then sometimes it don't work, but sometimes it works. Because in theory, this is something that should happen. But what we found is when we incorporate even some of our like Bacillus subtilis that produces antifungal compounds, but when we put in Trichoderma, the both of them seem to be able to coexist. This is something that we also don't understand. From a theoretical standpoint, in producing antifungal compounds, it should kill the Trichoderma, but the both of them are able to grow in the same carrier. So this is something that I feel that there is still lack of understanding of actually how the actual system works. I hope that answer your question. Yes.
I just have one question.
Mm-hmm.
I'd like to ask the future of applications of fertilizer. Do you expect something like one fertilizer
definitely there is no one universal solution for all different types of plants, because the plants itself, the physiology is different. Because we cannot expect to use the same fertilizer for paddy and then we use the same fertilizer for oil palm. It's definitely different because the physiology is different. The requirement is different. Even when we talk about NPK, the NPK formulations for different crops, it is different. And sometimes it is not just the nutrient requirement, it's more to do about geography. Geographically, we cannot say that the soil in Johor is the same as the soil in Perak. We cannot say that. Because that is why there is also an area of research more towards geoinformatics, whereby they do soil mapping. They do soil mapping to find out, even in the plantation, you could have, up on the hill, you could have high K. Down the hill, you could have low K. Or you can have high end on the hill, you have low end on the hill. So actually, if if we want to have optimum application, actually it is always different because the soil is different everywhere. But what we can try to do is we can try to come to what we call a balance. Let's say you need very high end here and very low end here. So that's why we call it formulations that go in the middle. So that because we cannot be asking farmers to, okay, on the hill you apply fertilizer A. Beside the river you apply fertilizer B. And then there you apply fertilizer C. Then it will be very confusing and it will also be very high cost, very costly. So personally I don't think there is one formula for all types of solution. What we can try to do is we can try to come to a compromise. For a particular set of conditions, we can use this particular type of fertilizer. Because problems are different everywhere. It is same. It not only applies to agriculture, it applies to us as well. Because there is no one medicine that can cure all disease. So this is something that we have to learn to accept. Because everywhere is different. I hope I answered your question. So any other questions from the floor? Yes.
I'm not so sure whether you have actually produced a product for fertilizer, oil palm, for example, combination of these three elements.
Mm-hmm.
Also number two, you're also proposing to use page to control bacteria.
Mm-hmm.
As you know that paste, sometimes you will also undergo life cycle, but also life cycle.
Yes.
If that happens, it will spread the DNA
Yes.
from one bacteria to another bacteria.
Mm-hmm. Correct. You're absolutely correct. But for our case, we are looking more towards the lytic type, not the lysogenic type. Because one of the reasons is, for us, it is easier to screen when we have a lot of samples. So that, I'm not saying that the lysogenic is not working. It's just that the lytic one, to a certain extent, it is easier to screen. Because this is an effort that requires a tremendous amount of effort to realize. And for your first question, we actually have fertilizer formulation that we co-developed with MPOB, which is called the MPOB F4. This is something that, because we to a certain extent we know what the market requirements, but the exact expert is still with MPOB because they have been doing research on the oil palm for so many years. So what we did was a few years back, our CEO Dr. Tony, he went to MPOB and he presented this. And it is not just input from All Cosmos side. It is a joint effort whereby MPOB is very open. If you have an idea on how to solve an existing problem that exists, then they would, if they are interested, they will also help you try to fill in the gaps. How can they use or modify your existing technology to improve the yield of oil palm. We actually have this product called MPOPF. Hope I answer your questions. So are there any other questions on the floor? Yes?
Do you ensure that these three components won't be leaching? Like previously you mentioned
Yes.
the fertilizer will leach and pollute the
Mm-hmm.
ground.
Mm-hmm. Leaching is caused by what exactly? Leaching is caused by high solubility, because when you use a single compound, let's say you use urea or you use ammonium sulfate, you put in water, you stir, it dissolves. But when you put in organic material such as compost, it does not dissolve easily. That is why the three, when we add together, and we either compact it into one body or we pelletize it, the organic material or the carrier material, it acts as a binder, which to a certain extent, it allows this control release mechanism. It's actually a very, very simple theory. If you have powder and if you have a granule, which one dissolves faster? If you have a powder, if you pour water, everything is gone. If you have a pellet, if you have a granule, or you have a tablet, then it does not dissolve so fast. This is actually a very simple theory. So I hope I answered your question. So are there any other questions on the floor? Kalinda? Kaina?
Waiting for them to ask you question. So what's your view on this sort of new thinking in agriculture, such as like farming or politics, positive or
I
direction?
mean that direction is actually very good, because like I mentioned earlier, one of the constraints that we have now is agriculture intensification. We have to clear soil, we have to clear more land. Once we clear more land, we lose more biodiversity. But if we are able to plant without clearing land, that is all the better. Then we are able to increase the yield without increasing the hectareage that we clear for planting. So that's why I mentioned earlier that fertilizer solves one part of the equation. There are so many other things that can be applied towards sustainable agriculture. All these like hydroponics, vertical planting, this is one way. Another way is also through better planting material, hybridization. Naturally, crossbreeding, plants that are able to resist drought, plants that have higher yield. Because there is no one solution. There's so many solutions. Because fertilizer cannot solve drought. If you don't have rain, fertilizer cannot solve it. I just want to quote a very simple example. In Vietnam is now one of the biggest rice producers in the world, a net exporter in rice. But what they are facing now, high salinity, because global warming. The tide is getting higher, seawater getting more inland. So salinity of the soil is getting higher. So when salinity is higher, you get lower rice yield. Because naturally, the hybrid that they use cannot tolerate high salinity. So this one will definitely reduce the yield. So there is a lot of effort in crossbreeding a new type of a hybrid that has higher tolerance towards salinity. And in fact, there are photos that show that you can even grow it to near seawater level. So this is I mentioned there's no one solution to a problem. That all these things must come together. No one person can claim only fertilizer can solve all the problems. Only pesticide can solve Only through planting this can you solve the problem. Because there are 1,000,001 different types of scenario, there are 1,000,001 different types of problems that require different solutions. But all of them, once if we are able to complement all this together, then and only then we can claim we have sustainable agriculture. Yes. Number 2. The fun one.
Mm-hmm.
Mm-hmm.
I'd like to highlight this is a very important concept in
Mhm.
nutrition as well.
Yes.
We're talking about
Mhm.
plant nutrition,
Mhm.
but
Mhm.
it's actually applicable to human.
Mm-hmm.
In agriculture, we care about, for example, a single
Yes,
field
yes, yes.
structure that is likely
Mhm, mhm.
because, for example,
Mm-hmm.
just select B1 fertilizer
Yes, yes.
in hingga or cycle, and
Mhm.
that will also lead to diabetes, for example.
Mm-hmm.
So
Mm-hmm.
I think the knowledge about nutrition
Yes,
is
yes.
compared to budget,
Mhm.
like the drive is more widespread.
Mm-hmm.
That we actually require human also for
Yes.
sustain our life, and as well as how we require all the elements, all the co-factors to drive our metabolism. I think if we can combine these two, we will create a sustainable living environment.
Even for lifestyle, it's all actually all this. The basic theory can a lot of times not just apply to one field, but it can apply to multiple fields. Even apply to humans. It applies to animals. Everything. Yes, yes, yes. I fully agree with you. Ask them question. So, Kami, Daniel.
Thank you, Mr. Charles, for his sharing knowledge with us. And ladies and gentlemen, as a token of our appreciation, we would like to give a small souvenir to guest speaker. To do that, once again, I would like to invite Yang Bahagia Prof. Muhammad Roji bin Samidi to present the gift.
From ICA, hopefully this time.
Thank you. Now we have come to the end session. I would like to invite all of us, firstly for the photograph session at the main stage, and secondly for lunch at the LED cafeteria. Thank you everyone for your time here.